is Arindam Dey, and I'm a PhD student at the Execution Lab in the University of South Australia. The paper I'm going to present today has been co-authored by two other persons, so Andrew Cunningham and Christian Sander, whom Dr. Sander recently is supervisor. So before going into the details of the paper, I would like to give you a brief overview of what we do in the field of Occluded and our lab. So in this video, you can see this visualization. So the girl is searching for a point of interest which is hidden by your building. So in the real world, you can see what's behind the building, right? But we have designed some visualization that makes you see through. So here's the cafe that's behind this building, and you can see it. So that's specific for outdoor applications. So now, why do it? So what's the motivation behind it? The first thing is handle augmented reality. So far in the augmented reality literature, it's all about always on the display, on the displays. So very few handheld display experimentations. While head-on display have some advantages and good application scenarios, but they are quite heavy and not very easy to carry and very big. So basically, they're not that suitable for outdoor applications for daily use. Conversely, the handheld display are very lightweight, small, easy to carry. Obviously, it's much cost effective than head-mounted displays. So we think that use of handheld displays can really accelerate the mass adoption of augmented reality in the market. So that's why we purposefully use handheld display for our prototype. We are the only person who realized that. So here you can see in the video is an augmented reality browser called Layer, and it comes pre-installed in Samsung smartphones. While this is a good work, but it has some limitations. First of all, they provide a few discrete set of informations, and that's over a very small screen. So it's a very hard to perceive the information quickly, particularly for the small screen. And there's another problem is how they visualize this type of buildings or point of interest which are occluded. So their approach is just showing this type of image, so you can see, but it really loses the context of the real world and the relationship between the occluded region and the occluded. So that's why we have developed a few visualizations, so see-through visualizations. So I have shown one before in the first slide, and now I'm going to show you two others. So this one is MEL, that MELs the occluded building in front of you and shows you the occluded region. So here you can see the cafeteria behind the building. So this is one example. Another way here points to the point of interest. And the other example is edge overlay X-ray, where we preserve the edge information of the program and can see through it and show the occluded region. So these visualizations are basically provides better context of the real world and the relationship between the occluded and occluded. But the problem with these visualizations, or not the problem, but like they do solve the same purpose, but they have some perceptual characteristics and which are quite different. And in this paper, we focus on those the evaluation of those perceptual characters. So how user can perceive the occluded region using these visualizations. So before going to our work, I'll just quickly go through a few of related work. So this one by Livingston et al. In 2003. So they have evaluated 3 different external data modes. So first one is the wireframe. The second one is a decreasing opacity, and the third one is a combination of both. And they found this one to be optimum or preferably better than others. But they didn't really use accurate depth perception, but they asked participants to identify which layer the target object is. So here is the target object. So they didn't ask participants to say the distance, but just the layer. This is another paper by Wither and Color in 2005, where they have evaluated a few different pictorial text schemes like shadow planes, top-down theme, and color-encoded markers. But the most influential related work for our current paper is this one by Livingston et al. In 2009. So where they have evaluated indoor versus outdoor depth perception in mobile augmented reality. And what they found is, in case of outdoor depth perception, it is always overestimation. But in the case of indoor depth perception, it's underestimation. So, and they also use graphical depth cube, which is like this tram line. So So here that you help in a particular situation, but not always. So, and yeah, so this is the most influential work. Why I will tell you later on. And there are some other extensive list of literature you can refer to the paper for that. So now let's get into the experiment what we have done. So first we asked participants what the task is. We asked participants to say the distance of this green object here. So the red circle was not there just to identify for you. So in the real situation it was not there. And we had a handheld display mounted on the tripod like you can see here, and it was connected to a laptop while we are presenting the experimental software. Okay, and the size of the green cube was 3 by 3 meters, and it was on a ground plane. So we had four main conditions. The first one is the visualization, which is the X-ray, and we use it as unique participant variable, so every participant participated in both of the conditions. And we had a queue. So queue was between subject participants. So one group participated in queue on, other queue off. And the property of the queue was each segment, each black and white segment of the queue is 10 meters. Now let's have a look how it looks in the real scenario. So this is X-ray without queue. This is male without queue. This is X-ray with queue. And this is male with queue. So these are the four conditions in our experiment. So now let's this is a list of the variables. So I have talked about visualization and depth queue, but there are two other distances. So we presented that green queue in 5 different five-field distances, ranging from 69.7 meters to 117 meters. So why we choose this long range is because of the application scenario of our visualization. So we intend to use it in outdoor locations, and like where people are searching for cafeteria or something like the city, it's normally at that range. And we then doubled the distance with the visualization to get 10 unique stimuli, and then we just randomly presented them to 3 times, so there are 3 repetitions. And the dependent variables were signed errors, so which is just the difference between perceived distance and the actual distance. So the positive signed error means overestimation, and negative signed error means underestimation. And there was also absolute error, which is irrespective of the distance, just the magnitude of the error. And then the accuracy, response time, and we also asked participants to subjectively rate our visualizations. So before the experiment, we had 4 main hypotheses. The first one was influenced by Livingston et al.'s work, so that depth will be overestimated in outdoor environment. And the second one is about our X-ray visualization, because it creates there's an amount of occlusion because of the edge overlay representation of it, and that we had expected it to have a negative performance over male. And male just conversely reduces all the occlusions in between, and it will perform better in terms of accuracy and response time. And the fourth one was about the depth queue. While our depth queue has a property of 10 meters each segment, so we expect participants to count it. So we expected them to increase the response time. And also we expected the alignment that we did trials, the response time will increase. Now let's have a look at the results. First, the signed error. So the most interesting what we found is that depth was underestimated, mostly underestimated, except a few conditions here in top, but it was mostly underestimated. And also the Q on reduced the signed error, so for both male and X-ray visualization, so it was helpful. And there was the main effect of distance on the depth perception. So basically, 117 meters distance was significantly towards than 82 and 69.7. So this was the effect on signed error, and we also counted the observations, or number of observations where there was underestimation or overestimation. So we found overall there were 600 trials, and only 411 trials were underestimation, and only 199 trials were overestimation. The most interesting thing here is, in only the case of male plus Q on, there was more overestimation than underestimation. expected, but Q on was, and it was more accurate for both X-ray and melt. But with increasing distance, what we found is melt was consistent, accuracy of melt was consistent always in the range of 90–95%, whereas with increasing distance, in the case of X-ray, the perception decreased, accuracy decreased. And we attribute this because of the edges that was presented on the scene, so it was very hard to look at the far distances and to count, especially count the segments of the depth cube. And now the response time. So as we expected, depth cube will increase the response time, and it did. But even in the one condition, melt was faster than X-ray. So this is melt was faster than X-ray in Q1 condition. It was significant. And we also found that in later trials, in Q-off condition, participants responded much faster. So here you can see it's a drop. And also in the case of Q1 condition, what we found is the response time decreased with the later trials, but accuracy was increasing or remained consistent. So that basically shows the learning effect of the depth cube. And we also asked participants to subjectively rate our visualization in 3 different aspects. One is the confidence, how confident they were in their depth judgment, and one is the visibility of the occluded region, and the other one was the usefulness of the visualizations. And in all 3 aspects, melt was rated higher than X-ray. And we also conducted NASA TLX, and it was similar task load for both of the visualizations, so there was no difference. So in summary, what we found is depth was underestimated in all conditions, and melt was better than X-ray, and depth cube increased accuracy and unfortunately, and as expected, response time, and subjectively melt was preferred over X-ray. Now comes the interesting part of our work is the contradiction with Livingston et al. So they found it's always overestimation in an outdoor environment, whereas we found it's mostly underestimation except the few cases. So this is a contradiction, and we have identified a few reasons for this contradiction. So first is the use of handheld display. So they used a head-mounted display, but we used handheld display. So that could be a reason of the difference. And the use of video see-through setup, whereas VRST' setup was optical see-through. And use of our image system, so which is more akin to virtual reality, because anything before the occluder was real, but anything beyond the occluder was virtual. So and we presented our target cubes in that region, so maybe that would be another reason. And the fourth reason is the longer distances. So they used distances from 4.83 meters to 38 meters, whereas in our case it was like 69 meters to 117 meters. And another effect was for the quality of our X-ray. So here you can see it is their work, and there was no such visualization like X-ray. So maybe that is another reason. So to conclude, so these are our core findings. So the contradiction with the previous work, that depth is underestimating augmented reality as well, not only virtual reality. And also we found melt is better than X-ray because of the nature of the visualization. We do some of the conclusions. And in the future, we would like to investigate further the reasons for this underestimation, and we intend to carry handheld display as one condition, and the other one is the distances. We want to overlap distances with their large distance and our smaller distances and something in between. And we expect a switch from overestimation to underestimation, somewhere in between 58 to 69 meters. Before I finish, I would like to acknowledge anonymous participants and other reviewers for their help, and this morning Brain Judges and Hanwin for their support during the experiment. Thank you very much.
Any questions for the speaker? Another reason for, or another
contradiction between your findings and the findings by Livingston may be grounded in the fact that they use stereoscopic visualization and they have no display. So I wonder if you could speculate about are you planning on using stereoscopic visualization on the actual device as well?
So when we are carrying on display and display, so that's one of the conditions so that it's stereoscopic. I mean, when we carry the technology display, so we are planning to use a stereoscopic display, which is part of the next study, and we are in fact already doing the study.
Any other question?
The next experiments that they use a non-split track, right? So assuming that get some additional tools for motion paralysis. In your experiment, you can start.
Yeah, we kept the static tested to avoid the tracking errors. That was one of the reasons. But in terms of egocentric depth perception, the main cue that plays the role is the distance in the visual field. The motion parallax is more like when you, for exocentric distance perception between two objects, motion parallax plays more role, but in egocentric depth perception is more like hypothetical.
Another one, from an application point of view, goes better, of course, underestimation or overestimation. So if I'm planning development, designing a mixed reality system, and which side I'd rather do?
That is really depends. So it's like how precisely you can. It will be the best will be if you can do perfect. So somewhere here. But if you are that off, then it's that. But if you that off, then it's okay. So yeah, it basically depends on the necessity of the first person, like perfect estimation.
Okay. Any other questions? Okay. If not, let's thank